channel. Today we're gonna work on the question, smallest string with swaps. It's a medium level question and the question states, you're given a string S and an array of pairs of indices and the string pairs where pairs I equals A, B indicates two indices 0 and that's of the string. You can swap the characters at any pair of indices in the given pairs any number of times. I think this any number of times is very important. It means we can switch back and forth any number of times. And if given many pairs, we can switch in between those pairs any number of times. So they're all connected. If they're all connected, we can interconnectedly switch them. I'll explain it further in the example they give us. So return the let's say graphically smallest string that S can be changed to after using the swaps. This just means we have to return the alphabetically smallest string that S can be changed to after using the swaps. Let's look at the example 1. So input S equals DCAB pairs equals 0, 3, and 1 and 2. 0 is D and 3 is B. This means D and B can be switched. And then 1 and 2 is C and A. This means C and A can be switched. So how can we switch this to make it the smallest, let's see, graphically smallest string? We need to switch B and D, right? So B comes before D, and then we can switch C and A, so A comes before C. The output should be BACD, which is BACD, and it's correct. Let's look at example 2. DCAB, it's the same string, and then now the number of pairs we can exchange is 0 and 3, which is D and B, 1 and 2, which is C and A, and now they added a third one, which is 0 and 2, and 0 and 2. This is very interesting because you see now 0 and 3 can be switched, 0 and 2 can be switched, and then 2 and 1 can be switched. They're all connected into one big set because they have something connecting them. So let's say 0 and 3 switches. Yes, now at index 0, and now 3 and 2 could be switched because 3 was at the original index 0 and 2 can, now 3 is at index 2, and now 3 can be switched with to 1, right? Because 2 and 1 could be switched, and that means they can all be switched, and we just need to sort them because they're all in one big component. So actually DCAB can be switched to ABCD because everything is connected here, and then since we can switch any number of times, we can just sort it based on how many sets there are. If there's only one set, it just means we can return the sorted lists. Look at example 3. So for CBA, the pair is 0, 1, and 1 and 2. Again, 1, 0, and 1, and 1 and 2. 1 appears twice here, so everything is connected again. So CBA can just be outputted to ABC because it's all connected and we can just sort it. So immediately we can see like this is a graph problem, right? And then this depends on if they're within the same set. So how can we tell if the nodes are in the same set? We can use a union find. We can union those nodes, these pairs together. We treat them as nodes, or vertices, and then we can check if they are all from the same set by checking their absolute root. Or we can, usually when I write a union set, I call it a parent dictionary. So if they all have the same, absolute and the parent, then we know they're in the same set, and then we can just sort that set. And we can start writing the code. So I'll start with writing a union find class. If you're unfamiliar with union find, you can look at my previous video on the video that talks about what is disjoint sets / union find, and I talked about union find solution with path compression, union by rank in detail there, and if you're confused on union sets. So first I'll initialize it with n. N will be the length, like the number of vertices, which should be the length of s. So that's 4DCAB. And I'm gonna write my union find using path compression and union by rank. So self.parent equals, parent assigns it to itself in the first time. So for I in range n, and then self.rank equals times n. Now I'm gonna write the find class. It's gonna take a node. What the the find function, not the find class. The find function does is it returns the absolute root of this node. So we know a node is an absolute root when it returns itself in the parent. So if node equals self.parent node, then it means it's an absolute root. We just have to return the node. Otherwise, we just recursively look for the absolute root, right? Now I'm gonna write the union function. Union function is gonna take two nodes, node 1 and node 2, and unionize them together. Since we're using union by rank, we need to compare the rank. But before that, we should get the absolute root of node 1 and node 2 first. So self.find node 1 and then do the same for node 2. And if they do not equal each other, that means they don't belong to the same component and we're trying to union them together here. So then we have to make an absolute root out of these two. So because we're doing it by union by rank, we need to compare their rank. So if self.rank root 1 is greater than self.rank root 2, that means we merge root 2 into root 1, and then we just merge it by updating the parent. So root 2's parent will now equal root 1, and if it's the opposite, we can merge root 1 into root 2. And in the other case that their rank equals, we can just default, it doesn't really matter which merges into which one, so you can default it into root 2 always merges into root 1 if their rank is equal. So now we can start writing our function in the smallest string with swaps. First we can create an instance of our union find that we just wrote, and then pass in the length of s as the number of vertices. And then after, we need to union these pairs together, right? So to do that, for node 1, node 2 in pairs, we can do graph.union node 1 and then node 2. And then after this, I'm gonna create a cut sats equals, I'm gonna create it as a default dictionary just because I don't want it to throw any errors. So from collection import default dictionary, and then it's gonna be a default dictionary of list. So for I and range, I'm gonna populate the set, which it's gonna map root, I'll call it the absolute root, to the characters in S. How do I say this? So the characters to all characters that belong to that absolute root. So all characters that belongs to that absolute root, including the root itself, because the root of, let's say the number 1 is the absolute root, and then the root of 1 is also 1, so the set will also contain itself, which is the absolute root. I don't know if that makes sense. So the characters are actually in S, and then so origins. Let me just write it first. For I in range length of S, sets, sets, we want the absolute root. So how can we find the absolute root? We can actually graph dot find I. So when we call this instance of this union find, right? We defined earlier as graph. So when graph we pass in the I, it finds the absolute root of I through this find function, and then that's gonna be the absolute root. And we're gonna store all the absolute root. There might be 4 characters here, but the absolute root, if in this case the absolute root should just be 1, right? Because everything is connected. There's only one component, so it can be 0 or 1 or whatever the highest rank is based on the higher rank. And they're all part of, let's say 0 is our absolute root. So all of these characters are part of this absolute root, and it'll actually actually only contain 0 and map to all its characters. So it will be this equals as I is the actual node of the character, and then it's gonna actually we don't want it to equal it, we want it to append si each time, so it can append all the characters to the graph. And then I'm gonna sort my components. Alright, I'll just write it sets. For I arrange length of sets. Actually, I don't need to do arrange for roots. For root in sets, root dot sort. So it sorts it in place, and then let me just make sure it's now sorted. So I'm gonna print my sets and see what it gives me from collections. That's root dot sort, and then let's look at our sets. Our sets is now mapped, the root is 0, and then the 0 absolute root maps B and D, and then the 1 absolute root maps A and C, which is based on the root, right? And now it's actually sorted, because before it's D and B and then C and A. Now it's sorted alphabetically. CB comes before D and A comes before C. So the next thing we have to do is actually so based on the each of the characters in S, we find the absolute root, and then based on the set class, we can pop the first one in the set going through our list. I don't know if it's my explanation is clear, so I'm just gonna write the code and then you can see what I'm saying. So for I in range length of S, we're gonna wait before that. Let's have a result list. Result is gonna be a list, and then for a result. Sorry, so I had to refilm this part because earlier, when I was doing it, there were some errors in my code. So basically, for I in range length of n, we append the absolute root to. We find the absolute root by looking for graph.parent I for that node, and then we look for the sets, the character that maps to that root in sets, which is already alphabetically ordered. We pop the first one, which will give us the most alphabetically ordered one, and then append it to our results. And our results will be a string, so we need to join
Please
the
let me
result.
know if you have any questions on the solution today, and thank you so much for watching.